In this lecture, we learn about NAT. NAT stands for Network Address Translation. And this network address, this private IP address, that network address will be translated to this public IP address. And why we are translating and how we are translating, that will be explained. Let's think about this A-class private IP address that is being used here, but outside that is just a private IP address, and this one cannot be understood in the external world. And this NAT, this one is NAT device, and this one is translating that the private IP address to public IP address, and that can be understood by the outside world. And later, that address, if this one is being sent through this NAT device to the other server or client in the internet world, then later that response will be back. Then the final destination is the public IP address. Here, this one is public IP address. And this one is translating to that original private IP address, which is sent that packet. Okay, all datagrams leaving local network have same single source NAT IP address. This one is public IP address, and this one, including this one, this side, this is one subnet, and they are using private IP addresses. Here, A class, any class, B or C, there are many private IP addresses. We can use any one of them. Here, we should focus on that. Source port number, that is in the transport layer. Remind, the field port number in transport layer, destination port number, and the source port number. That will be used, and we look at that in detail after reading this one. Here, datagrams with the source or destination in this network have this one for source destination, and this one is translating. Thus, this device or functionality that is called NAT device or NAT functionality, then may be embedded in the router. This functionality may be embedded. Access point in our home network that has this NAT capability. That AP has the routing capability as well as this NAT functionality. Okay, let's move to the next. Motivation. Why we need this? Because local network uses just one IP address. Okay, this one is public IP address. As far as outside world, we need this one, because outside world, the private address cannot be understood, as we learned already. And this one, range of address not needed from internet service provider, just one IP address for all devices. Think about our home network, just access point and some ADSL or cable modem, and to the outside world, this one is provided by the internet service provider. And this access point has that capability, this NAT capability. And here we can hook up line, Ethernet line, or wired or wireless smartphone or notebook. We can use in our home. We can change address of devices in local network without notifying outside world using this NAT capability, functionality. This NAT, as we learned already, this one is changing, translating that IP address for this or this. Even though those are private IP address, then may be changed to this outside world, and this is using just a single IP address, one IP address, that is public IP address. And this NAT device can change internet service provider. We can change ISP without changing address of devices in local network. We can change this internet service provider. We can subscribe other ISP, KT or SKT or LGU plus, and we can change. Even though we are not changing this side, we can just configure, then we can use. As we learned already, DHCP capability, and we can use the internet even though we are not configuring that IP address. And we can use same IP address for myself. Device is inside local net, not explicitly addressable and visible by outside world. In terms of security issue, that will be a kind of plus effect, advantage. Then how this one can be implemented? Before reading this one, more understandable figure is following. Thus let's look at that one first, this one. Okay, here, let's assume this one is sending host. Okay, I'll use the pen here. Okay, I'll use this color. And this personal computer, think about your house. You are using this personal computer and you are using this private IP address. And this host computer is sending datagram to the external server in the internet, and that is located somewhere in this internet, this server, and this address is here, 128, and so on. And then how that can be sent through that network, including this NAT or router containing that NAT capability. Okay, let's focus only the source IP address and destination IP address, and one thing more, that is port number. This 80, that means HTTP using the web service. This one is port number. This one is in the transport layer. Even though this one is transport layer, we are using here. And to differentiate the different computer or different devices in this subnet, we need to use this transport layers port number. And anyhow, that should be sent out through this NAT. Then how this one can be translated? And this one is the NAT translation table. Initially, that was this one, LAN side address, our internal as subnet LAN, and we are using this private IP address. And to differentiate these devices, computers, we need to use this different port number, and this one is using this 3345. And here, that should be stored there. This one is table, NAT table. And this one is assigning other port number here, and one private official, this one, public IP address, official IP address is here. At least we need to use this IP address here. This one is called NAT address. That is mentioned in next or in the previous explanation. That is public IP address. Thus we are using this public IP address. This one is official, and that is unique in the world. Thus this one is, this original datagram was this one is changed to this. The datagram contents payload, that will be same, but the source address and destination address, among them the source address is being changed to this instead of this. Later, when this one is responding, then this one will be the destination address. Then properly this one will be arrived there, and also this NAT is translating that address after receiving that response from this one later. This one is the source address of this one, same, and this one is destination address, and the same here. And that will be translated because we have that translation table here. That is called NAT, translation table. Referring to that, that is being changed to this one. Thus, that can be arrived there. Okay, this one is explaining. Reply arrives destination address here, and the NAT router changes datagram destination address from this one, as I mentioned already, from this one here to this. That is for that. And the others should use different port number when they are, this one is sending another datagram, also this one is sending another datagram, then this one is using another port number, different port number. Different port number. Okay, let's move to the next. Okay, we just skipped one slide, thus we'll be back here. This one is explaining the previous explanation. This one is the description for that. Okay, let's use the pen here, red color here. NAT router must outgoing datagrams. NAT should replace source IP address and port number, as we learned, of the every outgoing datagram to NAT IP address. NAT IP address, that is, as I explained, public IP address, and officially unique and understandable by the outside world. And new port number, as we learned. A remote client server will respond using NAT IP address, that is public IP address, and new port number, that is translated one as destination address, and that will respond using that destination address. And this one is remembering in this translation table every source IP address and port number to NAT IP address, new port number, translation pair. This one is containing. This table is containing that information there. That will be changed back. Incoming datagrams. NAT will replace the public IP address, new port number in destination fields of every incoming datagram to corresponding. This is private IP address and port number, as we learned already. That is stored in this table, NAT table. Okay, let's move to the next. We learned already here. And this one is explaining a little bit more about the NAT. NAT is using 16-bit port number. And this 16-bit port number field is 2 to the power, okay, we should use this pen. Okay, 2 to the power 16, because this one is using 16-bit port number. And this port number is in transporter layer. This is around the 2 to the power 16 means over 65,000 simultaneous connections with a single LAN side address. NAT is arguable, controversial. Routers should only process up to layer 3. Let's think about our definition about each layer's functionality, and that is modular design. And the network layer, that function should be confined to layer 3. And this device is network layers and the layer 3 device, and that should use layer 3 protocol fields and any layer 3 related information. But this one is using port number, as I mentioned, that is layer 4, transport layer port number. Thus, this one is breaking our design concept of this layered architecture. And address shortage, if we have address shortage of IP version 6, then that should be solved by our idealized IP version 6, and that is offered already. And we are going to this IPv6, and also we are able to use this one because that is standardized already as soon as possible. And this NAT functionality is violating end-to-end argument. NAT possibility must be considered or taken into account by application designers. For example, peer-to-peer application, that NAT functionality that should be considered. This is application layer. Why this application layer is considering the inside deep layer 3 network layers functionality. And also NAT traversal problem. What if client wants to connect to server behind NAT? Whether there is NAT or not, depending upon that is called NAT traversal. And we should consider that. For example, for VoIP, whether there is NAT or not, depending upon that, we should consider. That is called NAT traversal. Okay, next topic in this subchapter 4.3 is about IP version 6. Let's move to there. Next slide. Okay, let's use this pen. Okay, IPv6 motivation. Why we are using IPv6? Still we are using IPv4, even though that is successful. Why we are trying to use this IPv6? That is standardized already. The middle of 1990s, almost 25 years ago. Still we are using IPv6 and some migration to IPv6. initial motivation is 32-bit address space. That is, address space is like this. That address space soon to be completely allocated. Already that is allocated. Already completely. Almost around 10 years ago. And the additional motivation is header format helps speed processing and coding. Header field in this IPv version 4, IP version 4, think about some option field and some redundant fields. Initially that was good design, but actually some fields are not being used well. And some field is degrading the performance, but now the network speed is increased a lot rapidly, and this protocol should be using that capacity of their bandwidth. Header changes to facilitate quality of service. This is quality of service. IP datagram formatters finalized, and that is already standardized, and fixed length 40 byte header. And we learned about some fields about the fragmentation and reassembly in IPv version 4. Think about some code and some flag and some offset. Those are all related to these fragmentation and reassembly. But that is not very good. In this IP version 6, there's no fragmentation. Then how we can send big datagram? That will be discussed in the next slide. Let's look at this IPv6 datagram format first. Okay, this is version number, and that is 4-bit. There's if we are using IPv4, then this number is 4. Then, as I explained already, this one is 0100. That is 4 in binary format. If this is version 6, then that should be like this. Here. And this is priority, and this one is identifying priority among datagrams in flow, and that will be explained a little bit more in detail later. And let's look at this flow label. Even though that is not well defined, the basic idea is about the label for flowing. Think about some video stream like Netflix video stream or YouTube video stream, and even streaming game video stream. That kind of application was considered. Even though at that time that was not exactly considered, but this one is roughly that may be needed to differentiate that flows using this flow label. Thus, this one is identifying datagrams in same flow with the same flow label. Next header here, that is mainly to identify upper layer protocol for data. This IP upper layer is TCP or UDP, that can be identified. And top limit, that is same to the TTL in the IPv6, 8-bit. There's whenever this one is going through one router, that will be decremented. This initial TTL value will be decremented, -1, and it is repeating. And if that is being 0, then this datagram will be thrown away, and it is not going through that network forever. This one is payload length. The size of this one is the payload. And so simple in terms of the number of fields and the kinds comparing to that IP version 4. And the others, even though this one is 40 byte, that is twice of that IP version 6 basic datagram header size, 40 byte. Most of them, this one is 128 bits. That means that is 16 byte. This one is destination address 16 byte. That is 128 bit. Another, this one is 32 byte. This one is 4 byte, 8 byte here. Those are in total 40 bytes. Thus, IP version 6 datagram, this header size, that is 40 bytes fixed. Okay, other changes from IPv6. Checksum. Please remind the previous IP version 4, we used the checksum to check that error, and we should calculate that checksum, and that is removed entirely to reduce processing time at each hop or each router. Whenever that is going through, that is being checked with this checksum. Thus, that means that checksum field that was calculated, that calculation, it is degrading the performance. It is reducing that performance. It is reducing that processing time. Thus, that is removed. And option field. Think about option field. 20 byte basic in IPv version 4, and another optional field that is around 40 bytes. That may be optional field, but those are here. Not used here, but allowed in different way. How? But outside of header, indicated by next header field, that optional contents can be put in, but using this next header field, that may be used for that. Thus, this next header field that can be used for option, or let's go back, to identify upper layer protocol for data, that may be used for both. ICMP, okay, let's use again this pen. ICMP, Internet Control Message Protocol, version 4 we learned, and not in detail, briefly we learned, but later we learn about this in detail. Anyhow, this one is explained about IP version 6, and that ICMP version 4, in the ICMP, even though that is not attaching any postfix here, like V6 or V4, this means IP version 4 ICMP. New version of ICMP. This one is providing this capability, additional message type. For example, packet too big and multicast group management functions. Those information and the functions that is possible here. That is new version of ICMP. Then the question is, we are now using IP version 4 mainly, and IP version 6, that is our future, but we are migrating. Smooth migration is required, smooth transition from IP version 4 to IP version 6. How? Not all routers can be upgraded simultaneously. That means we cannot suddenly change to this IP version 6 one day. We cannot do that. That means no flag day. How will network operate with mixed IP version 4 and IP version 6? Anyhow, these two versions will be mixed, and we are using both of them during that transition period. Then this concept, tunneling technology, that may be used for that transition period. IP version 6 datagram carried as payload, as data in IP version 4 datagram, embedded in IP version 4 as data. This one will be embedded there, and that will be sent through that IP version 4 routers like this. This one is IP version 6 datagram, IP version 6 header fields here, source destination, and data here, and those are all embedded here using this IP version 4 envelope. Then we can send through this IP version 4 internet infrastructure. Okay, let's move to the next. This one is explaining a little more in detail about that tunneling. Okay, here I'll use this pen. Here, logically, IP version 4 tunnel here. This one is IP version 4. Even though this one seems to be small, our major infrastructure is based on this IP version 4 infrastructure. And some portion we are using this one, and the statistics will be shown in next slide. Anyhow, here let's focus on this IP version 6 here router, IP version 6 and IP version 6 and IP version 4 capable router. Also, this one is one side is IP version 6, another side is IP version, this one is IP version 4, another side is IP version 6. This device is being used. This is IP version 4 here. This one is the tunneling and the packet. Okay, let's look at next one. Okay, this one is showing completely. Think about the fields in IP version 6. We are using flow, and those flows are being shown here. This one is IP version 6 datagram, A to B here. Final destination is F here, but intermediate B to E, the IP version 6 datagram can be understood. Also, this one can understand, and that will be embedded here. And the envelope, that is IP version 4 header from B to E. This B and E can understand IP version 6 and IP version 4. Those headers can be understood by this. This one is extracting only that inside IP version 6 datagram, and that will be delivered successfully. Let's move to the next. This one is explaining about the adoption of IP version 6. This one is probably status about 5 years ago, And this slide was made almost 5 years ago. And today's 8th version, this is 7th version, 7th edition slide. And we are focusing on this. Thus, I will explain this one first, but for reference, for better understanding about the current status, I will borrow some slide from the 8th edition, but you don't need to worry about this, just for reference. I'll not ask about that in the quiz test or even in the exam. Google is 8% of clients access services by IP version 6. Google is, okay, this one is introducing IP version 6 adoption by Google, around 30% of clients instead of 8%. And this slide was made recently. There's after 5 years from the previous slide. And from the mid 1994 actually, that is after around 25 years. And next slide is more recent one. Still this one is showing IP version 6 adoption, but the day of October 11th in the year of 2020, this year. And you can refer to these statistics in this website. And this is from 8th edition. And this is just for reference, for better understanding about the current status of the IPv6 adoption. The statistics here, that number is here 32, okay, here 32.26%. Google users, among Google users, the statistics are showing deployed more in terms of this IPv6 adoption. Let's move to the next. Okay, this one is still explaining about that. And this is changed. Instead of 20 years ago, and this one is being changed to 25 years ago, because this one slide is made recently. Okay, I'll use this pen. Since the mid 1990s, after 25 years now, as I explained already, many services, internet services are successful, even though that success, why? Still we are using mainly IPv4 instead of IPv6, even though that is introduced so long time ago, around the mid 1990s, almost 25 years ago, that IPv6 was introduced and standardized. Okay, let's move to the next topic. That is the final subchapter in this chapter 4. 4.4 is explaining generalized port and software-defined network. Okay, generalized porting and software-defined network. Here, each router contains flow table that is computed and distributed by logically centralized. We learned about this concept already. This control plane that is aggregated here and logically centralized here. This is called control plane, and this one is related to the software-defined network because that is being used, and they are configured using the software. And this one is data plane. Simply this one is porting. Here, more generalized porting in general terminology. Thus, this one is called local flow control, flow table instead of porting table. Porting capability is embedded here. Values in arriving package header, depending upon that will be going out, depending upon that flow table. and that flow table will be updated by this logically centralized routing controller, and this is called control plane. This is OpenFlow standard name and the data plane abstraction. Flow means, and that is defined by header fields. And instead of porting, this is called generalized porting. I'll use this pen. And simple packet handling rules. Here. Pattern match. We are checking the matching of that pattern. Match values in packet header fields. And the actions for match the packet. Depending upon that, we are doing some action. One action may be drop, or port, or modify, or match the packet, or send match the packet to the controller. That is another action. Just sending that matched packet to the controller for logging purpose or for analysis. Simply this one is dropping that packet, porting packet, like our ordinary router, and modifying like our NAT. NAT is modifying, right? The IP address and the port number. And the priority. If there is some overlapping patterns, and there are many, then depending upon their priority, we can differentiate, disambiguate. And the number of bytes and the number of packets can be counted using that counters. And the flow table in a router, and that will be computed and distributed by controller, as we learned already in the control plane. And that flow table define router's match and action rule. And we look at that example in detail here. Flow is defined by header fields. Thus, we are looking into that header fields. Which header? Layer 2, layer 3, layer 4 headers. Those headers can be checked. Generalized porting means simple packet handling rules, as we learned already. And this one is the example for that. This one is repeated here. This one is checked whether that is being matched. Here this asterisk means wildcard, any number, any IP address of that field here, of that part of that IP address, anyone. Then that datagram, that packet will be dropped. If the source IP address is like that, anyone, and destination IP address 3.4 and the next one is anyone, then that will be forwarded to the physical interface port number 2. And depending upon that match, this action. If we want to log to analyze this packet, then some specific packet from this source and any destination, then that will be sent to the controller for logging purpose or analysis purpose. There's, depending upon that, the header field here, we are looking into this, considering this header. Okay, let's look at this pen every time that is being changed. Data link layer header can be checked. This is called Ethernet frame header, and this one is network layer IP header. This one is transport layer header, Among them, some fields are considered here, transport source port or destination port in this transport layer, and we can use that field to check. And the action is, if that is matched depending upon our matching field, and the action will be done. Depending upon this action, that will be done. Forward packet to port, or encapsulate and forward to controller, drop packet, like that. Statistics, number of packets or bytes that can be counted. Okay, this one is a more specific example using that match and action. Here, okay, let's look at this pen. IP datagram destined to IP address, this one, should be forwarded to router output port 6. This is action. This is physical interface port number, not transport layer port number. This one is physical router's physical interface 1, 2, 3, 4, 5, 6. Then that is the port number for that. The packet can be go out through that port number. If that is matched in this way, only IP destination address is being checked, and the others don't care. And do not forward block, that means block, that means drop. This packet, if that TCP destination port number is 22, then that all of them will be dropped. Blocking, we can do that. And also this one can be dropped depending upon the IP address source number. If some suspicious and strange and malicious computer, that IP address is this, and from that IP address any datagram will be dropped. We can make that action in that way. Okay, this is another match and action example. Here, this one is checking. Okay, let's look at this one. This one is checking this Ethernet. This MAC means Ethernet address. You can think in that way. Ethernet address. The Ethernet address is here 6 bytes. We learn in chapter 6 in detail about this. That will be checked whether that is being equal to this or not. Depending upon that, okay, if that is matched, then that will go out to the port number 3. Okay, this one is explaining and repeating again some portion. Match plus action unifies different kinds of device. This concept is so generalized concept and applicable for other application in uniform way using the software. Thus, this is called software-defined network. This one, router or switch or firewall, those are all isolated and standalone different devices. But using this concept, this abstraction, we can unify different kinds of devices using the software-defined abstraction. Router, simply longest destination IP prefix address is matched, then port. And the switch functionality can be implemented using this abstraction. Match destination IP address instead of IP address, here MAC Ethernet address. Later we learn about that in chapter 6. Then action is forward or float. Firewall. Firewall is checking IP address and TCP UDP port number for security issue, protection. Action is permit or deny. NAT, as we learned already, if that IP address and port number, this is private IP address or public IP address and port number, that will be translated. Action is rewrite address and port number, as we learned. Those NAT functionality also can be implemented using this OpenFlow abstraction, using the software. Thus, this is called software-defined network. Okay, this is a more specific example. For example, datagrams from host H5 and H6. H5 is here. H6 is here. Should be sent to H3 or H4. H3 or H4 via S1, switch 1, and from there to S1, S2. Here and to S2. Not directly to this one. Thus, that should go through this one. Okay, I'll change the color of that pen. Okay, here, and then for that application, that example, the purpose is this, goal is this, then we can implement it in this way. Match plus action, match here. IP source port number here, another source port, IP address here, source address and destination address from this, and destination is this, 10.2 here, 10.2 here, and the source is 10.3, 10.3, and the others don't care. We don't care about that. Then that should be ported. This is the port number, the physical interface port number. This one. That datagram should go out through that link. Here, match ingress port number 1. Ingress means input. Input this one. Ingress this input port number 1. Datagram is incoming through this interface 1, and the IP source is 10.3 and the destination is 10.2. Then those packet datagrams will go out through this port number, link port number, ported. And here finally in this router, that will be checked, match. Ingress port number 2, as I mentioned, this is input port number 2 here, and the destination port number 10.2, and more specifically 0.3 here. That is the destination address. Then that should go out through that link port number, interface number 3. The other ingress port number same, and the destination address is 0.4 here. Then they should go out through that interface port number 4, like this. That is the action. Okay, let's move. Let's think about the intelligence. This one is from okay, I'll use this pen. This one is from 8th edition PowerPoint. I just borrowed. You don't need to know about that. I'm explaining for your better understanding about the current status of this technology, about the network infrastructure of that intelligence. Here, 20th century phone network. Initially, our telephony technology since 19th century, 1876, Bell invented the telephone. After that, around the 1960s and 1970s, personal computer introduced, and 1980s, PC, Unix machine, those are introduced, and C language even, those are introduced. And personal computer actually, mainframe, that was introduced around 1943, around ENIAC computer, and around 1950 in the history of this IT industry, the IBM's mainframe, IBM 60, IBM 70, and so on. and personal computers in 1970s introduced. And during that time, this one is so complicated, and this means brain, intelligence, and this one is not having any intelligence, just dumb terminal, dumb telephone. Think about your telephone, about intelligence, and compare to the PC or smartphone. No intelligence, right? And inside of the network, infrastructure has that intelligence. And for that intelligence, because of that emergence, the evolvement of that microprocessor that is introduced around the mid 1970s, and computer, personal computer, and those are possible. And this one was mainly developed by Bell Lab, AT&T Bell Lab. Bell invented this one, and this is Bell Lab using this name. And this intelligence, for that intelligence, they need some special language, the C, and special operating system, Unix. Those are invented by this telephone research laboratory, Bell Lab, around the 1970s and the 1980s, around that time. And here internet is introduced, and you think about your PC and the smartphone. People, this one is before the smartphone. Smartphone is initially, that was around 2007. Steve Jobs introduced that. Before that, feature phone, and now that server or personal computer or notebook, and those computers and the ending node device has some intelligence at the edge device. Here, intelligence computing at network switch inside, and intelligence is here at the edge part. Later, we are using some data center, big data center, and even in the network infrastructure, we are using software-defined network. Thus, this one is using and implementing some intelligence here. Thus, intelligence is located and distributed. After 2005, programmable network devices, intelligence computing, massive application level infrastructure at edge. Even in the inside, intelligence is there. Okay, that's it. This one is summarizing chapter 4. We learned about the overview of network layer, data plane, and the control plane. And what is the, let's look at this pen. What is inside the router architecture, we learned a little bit. And internet protocol, we learned about them. And the generalized port and the SDN. In this lecture, we learned about the match and action. Question is, how to port? How do port? Tables. That means destination-based porting or pro table generalized porting computed. Answer is by the control plane. And the next chapter, chapter 5, that is mainly about this control plane. Still we are in the network layer.